In this video, we are going to look at nuclear power. A nuclear reaction involves the nucleus. Nuclear chemistry involves the nucleus. And there is so much energy that is associated with these nuclear reactions. So, nuclear power plants can use nuclear reactions to create steam and generate electricity. In a nuclear power plant, we can have a reactor core, fuel rods, and then these different steam lines. The reactor core generates heat by a nuclear reaction that is called nuclear fission. And this is where you have a large nucleus and it splits into smaller nuclei. What's neat about this is we can get a chain reaction. So you can start off with this one really big nucleus, bombard it with some sort of energy and some sort of particle, and it can split into multiple nuclei. And then they can do the same thing, and they can do the same thing, and we get all of these chain reactions. A way to control this is we can use boron rods and it absorbs neutrons produced during the fission, and this will prevent a chain reaction. There is also the ability to regulate the number of uranium atoms undergoing the fission process. So if you don't have a lot of uranium atoms, then you can't have this nuclear reaction continually go. Nuclear fusion is kind of the opposite. So you have two smaller nuclei that form together to make a heavier nucleus. This process releases way more energy than fission reactions. However, we do not currently have any fusion power plants. There's no fusion reactors. And the type of chemistry on the sun is a nuclear fusion reaction. The military can also use this nuclear reactions, and there is something that is called enriched uranium. And your enriched uranium is when we have the concentration of uranium 235 has been increased. In a nuclear reactor, there is approximately 3 to 5% of uranium 235. With crude nuclear weapons, that increases to about 20%. And with modern nuclear weapons, that increases all the way up to 85%. We can measure the critical mass, which is the amount of uranium 235 needed to produce a chain reaction. So if you don't reach that critical mass, then you're not going to start the chain reaction. So if you don't have that critical mass, then you can think of it as the uranium has been depleted. And depleted uranium metal can be used to make armor-piercing missiles, and this is due to uranium's really high density. Neutron activation analysis, or NNA, which is a way to analyze what is present in a sample, if you will. So, transmutation, which is the process of a stable isotope being converted into a different element or isotope. And this process is used to make radioisotopes, and these radioisotopes are a lot of times used in medicine. And transmutation occurs and the radioactive isotope is formed, and then the isotope will emit a gamma ray that can be used to identify what element is present in the sample. So this little figure here shows the process that the neutron activation analysis can undergo. This was used to determine that only two bullets hit President John F. Kennedy when he was assassinated. It's also was used to determine that President Zachary Taylor was not poisoned with arsenic. Now, nuclear chemistry can also be used in a very terroristic way. And it's very important that we understand the different attributes of nuclear chemistry so we know what to watch out for.